All right, we want to look at what is called continuity, which is what does it mean for a function to be continuous? Now, first, I want to give you an informal definition that you can think about. Now, we're going to have some definitions and theorems here in this section. And when we get to our definition and theorem quiz, you're going to have to remember what the definition is. So what I'm going to say with the informal, this is not the definition you want, right? This is not what you want to put on the quiz. I probably would take off more points than it's worth just out of spite if you would write this down. But this gives you the best idea of what we're talking about. So what is continuity? Basically, a function's continuous if you can graph it without lifting your pencil. That's all it means. So if you can graph something without having to lift your pencil, then we say that function is continuous. That's all it is. So if you look at the graph we have here, could you graph that without lifting your pencil? No, because if you tried to do this and you said, okay, I go to here, what's the first thing you're going to have to do? Lift your pencil to go to there, right? So you couldn't do it. And even if we got here, you have to lift your pencil to go to there to come back. So that's like the informal idea of what it means to be continuous. So when we talk about continuity, that gives you a good picture in your mind of what we're talking about. But what is the actual definition of continuity and continuous is this. A function f of x is continuous at a number a if the limit of f of x as x approaches a equals f of a. That is our definition. A function is continuous at a number a, so that could just be some number, if the limit of f of x as x approaches a is equal to f of a. Or another way to say that, if the limit equals the functional value, it's continuous. Okay. So, let's look at an example here at our graph. If we look at where it's continuous, let's say at 1. Does the limit at 1 exist?
No.
No. Why no?
Because they're different.
Which is theorem Bob. So from the left and the right is different. So this doesn't even exist. So the limit doesn't even exist. We don't have to worry about the function. Is the limit equal to the function? The limit doesn't exist, so this isn't even possible. Okay. Consider at 3. What is the limit at 3? Which is 2, right? And then what's the functional value at 3? 2. Limit equals the function value. So at the point 3, you could graph that there without lifting your pencil, right? That's the idea. Another one. What about at 2? What is the limit at 2? Well, you approach from the left and the right, you get 1. But what is our functional value at 2? 2. So here's the 3 things that can happen. 1, your limit doesn't even exist. Or the functional value doesn't exist. Something does not exist. Therefore, it's not continuous. 2, they both could be equal. Check mark, it's continuous. Or 3, they both exist, but they're not equal. That's the idea of what it means to be continuous. Now, we do have this situation where, like right here, the limit from the right is also equal to the functional value, right? So we're going to have something called continuity from the left and the right. Okay. So the idea here is if the limit from the right equals the function value, then we say it's continuous from the right. If the limit from the left equals the function of value, then we say it's continuous from the left. To be continuous at a point, the limit has to exist, so the limit from the left and the right have to exist. The left and the right. So, what does that mean? This graph is continuous from the right at 1, right? The limit equals a function of value. It's also continuous from the left at 4. Now, why is it not continuous at 4? Well, there's nothing to the right of 4, right? So the limit at 4 doesn't exist. But the limit from the left exists equals a function of value. This over here, the limit from the right at 0 is continuous. And then here you could see, like at 2, the left and the right aren't equal to the function of value, so it's not continuous there. Okay. All right. So let's talk about how this can happen when we look at graphs. Now, I copied this out of the book. I don't like the way they do it, but we'll just go with it anyway. So, types of discontinuity. And here's the first type of discontinuity. It's not really a type of discontinuity. A function can be continuous. So these are kind of like things that can happen. One, you could have a continuous function. So you have a function that you can like graph without lifting your pencil, right? All of these kind of graphs are continuous. When we think of things that are continuous functions, lines, polynomials, some trig functions, exponentials, logarithms, right? All of those are continuous. You can graph them without lifting your pencil, right? Now, this is not, we have vertical asymptotes, we have nothing like that for these, okay? Those are all continuous. Most things that we work with are continuous, which is good, right? Continuous is going to be kind of a condition to a lot of our theorems and rules. It will say, well, if you have a continuous function, then you can do this, this, and this, right? I'm looking on the back wall right there, the fundamental theorem of calculus, which we'll eventually get to next semester. But it starts out for every continuous function. So this is kind of like, if it's continuous, that means it's nice. I always say it's nice. It's well behaved. Nothing crazy is happening, right? There's no holes and jumps and all that kind of stuff going on. All right, the next one. Removable discontinuity. Number 2, removable discontinuity basically means there's just a hole in the graph. It looks like somebody reached in and removed one point. And then you see in your notes there's actually 2 places to write this. So there's a number 2 up here in the list, but then there's also the number 2 that goes over it. It's kind of connected. So we're going to connect these with these different graphs, right? So the second one is removable. Just a single hole, somebody removed out. Okay. Our third one is jump discontinuity. So we have removable, we have jump, and a jump discontinuity kind of looks like this. Which the graph does what? It takes a jump. There's a break in it, right? So that's jump discontinuity. That one you can kind of see. Our fourth one is called an infinite discontinuity, or that you can also think of that as just a vertical asymptote. The jump discontinuity is a vertical asymptote. And the last kind of discontinuity we have is something called an oscillating discontinuity. And this is just kind of like craziness discontinuity. Like if we would look at sine of 1 over x, here, let's go with this one. This one's kind of cool to look at. So if you graph sine, you get that. Let me, so look at that graph, and there's kind of a break in the middle, right? But watch what happens if I zoom in on that. Let's say I go from -1 to 1. It gets crazier. Let's say I go from -0.2 to 0.2. It gets even crazier. Like the more you zoom in, the crazier this graph is. Right? Now, kind of give you an idea what's happening here is, let's say we wanted to look at a graph, and we are going to go from -0.001, that would be the positive side, I know how graphs work, -0.001. So let's imagine we're zooming into those two numbers, okay? So if I go back to my calculator, and we go -0.001 and 0.001. Now, if you think about a graph, I think you would agree that's pretty zoomed in, right, around the origin, right? But understand what our graph is. Our function is sine of 1 over x. So when you put 1 over 0.001 in, this is like 1,000, right? This is going to be like a -1,000. So what does that mean? I look at it like this. That distance right there is 2,000. And do you remember the period of sine? It's like 2 pi, right? So our normal sine curve right, looks like that, right? Now, between -1,000 and 1,000, we have 318 sine curves. So what that means is between -0.001 and 0.001, in that window, we have 318 complete sine curves going back and forth. And here's where it gets even crazier. Think about if we went somewhere smaller. 1 divided by 0.000001. And you divide something like that by 6.282 pi. The closer you get to 0, look how small that is on your graph. Think about where 0.00001 is, and then the origin to 0. And in that little tiny window, you have 160,000 full sine waves. This graph is just going like crazy when you get close to the origin. We can't even graph it because there's just so much going on there. It doesn't exist at 0, and it's just this crazy oscillation. So it's just kind of a weird function. Okay. All right. So let's look at an example here. Let's start that tomorrow. I'm going to look at something else here. Let me bring this up. It's going to take us longer than the time we got left. Delta math homework. Let's just look at a couple of the kind of questions you're going to get. You can start doing some of these. So, graph shown, state the values of x which has a removable discontinuity. So if you look at the types we have, right, which one of these has a removable discontinuity? So the ones you have, we have a discontinuity at -5, 1, and 3. Which one of those are removable?
-5.
Is -5 removable? Or it jumps? Right? See how it goes from here and jumps? That's a jump. But look at 3. 3, just you removed a single point. 1, you removed a single point. Does that make sense? That's removable. When it has a break like that, that is, that would be a jump. Let's see a new one. There, where's our removable at? 3 and -4. Okay. Okay. Now this one's asking, where is the jump discontinuity?
-7 and 7.
Does that make sense? See, does that make sense now what you're looking at? So that's the first kind is like this. I don't know. Okay, there it does. Where's the infinite discontinuity? -5 is where you have a vertical asymptote. So the first couple problems here are just understanding those different types of discontinuity, right, from the graph. Says use the definition. It's going to actually ask you to got a whole look at all the stuff you got to fill in here. So let's look at this. So it says use the definition of determine whether f of x graph is below is continuous at 0. So it's at 0. So the question is then, since what's the limit from the left of the function at 0?
4.
-4. And what's the limit from the right?
1.
1. With me? It can be determined that the limit of f of x as x approaches 0 does what?
Not exist.
Does not exist and is equal to, and if you click not exist, the equal to goes away. Furthermore, it can be seen that what is f of 0? In this one, there's no dot, doesn't exist, right? Therefore, it can be stated that the function is not continuous because at 0,
The first one.
the limit doesn't exist, and then you can, okay? So you're just kind of using that definition of the limit existing and the function of I. Let's look at another one. So at -2, that's going to be very similar. Let's see if we can find another one that's a little different. Okay. Here, at -1. What's the limit at -1 from the right?
1.
From the left?
1.
1. Does the limit at -1 exist?
Yes.
Yep, it's equal to 1. And then what's the functional value at -1?
1.
1. Therefore, it is continuous because the limit is equal to f of -1. So this is just kind of understanding that definition that the limit at the value equals the functional value. And so you just kind of click through that, okay? The other ones, I don't know if we can, yeah, we haven't got to those. So you can click through the first two. They're just kind of looking at the graphs if you want to get ahead, or you can just wait, whatever, right? So, but I wanted to at least look at those. That's kind of what we've gone over today.